For decades, we really thought we had it all figured out. Late blight. This is the disease that caused the Irish potato famine, a truly devastating force of nature. But hey, we had a plan, a rule book, and for a long, long time, we believed that just following that rule book guaranteed control. Turns out, that belief, that whole sense of security, well, it was basically an illusion. Okay, this one sentence right here, this is the heart of our entire explainer today. It really marks this fundamental shift in how we understand the fight against not just this disease, but any complex adaptive threat. It's that aha moment where we realized our perfectly laid plans were being completely ignored by the one thing that actually mattered, the pathogen itself. And this rule book, you see, it was built on what felt like this unshakable foundation. 3 core strategies, right? 3 pillars that promise to keep Phytophthora infestans, that's the bad guy behind late blight, firmly in check. It was our shield. It was our playbook for victory. So let's break them down really quick. First up, perfect timing. The idea was to spray fungicides exactly when the weather conditions were just right for an outbreak. Second, resistant plants. Pretty straightforward, right? Just breed potato varieties that can naturally fight off the disease. And third, smart chemistry. This meant rotating different fungicides so the pathogen could never get used to one and develop immunity. It sounds foolproof, doesn't it? A perfect 3-pronged attack. But that is the billion-dollar question. Because here's the thing. While we were busy perfecting our rulebook, the enemy was, well, it was evolving. This pathogen, Phytophthora infestans, it wasn't some static target sitting still. No, it was a dynamic, rapidly changing opponent. And it was about to expose the fatal flaws in every single one of our pillars of control. Okay, so let's tackle that first pillar, timing. For years, the whole strategy relied on weather forecasts. If the forecast said warm and humid, we'd spray. Simple as that. But as we found out the hard way, that's kind of like planning a massive defense without even knowing if the enemy has crossed the border. This slide really breaks it down beautifully. See, a climate model only tells you if the conditions are good for the disease. It predicts the opportunity. Think of it like this. It's asking, are the roads clear for a getaway? But an aerobiological model, which, get this, actually samples the air for the pathogen's spores, it confirms the threat. It answers the real question. Is the getaway car actually on the road right now? And when they did this, the results were absolutely stunning. A study in Spain found that when they combined the weather data with this real-time spore tracking, their prediction accuracy for an outbreak just skyrocketed to over 90%. That proved it right there. Knowing the conditions just isn't enough. You have to know if the pathogen is actually in the air. All right, so timing is flawed. We get it. But what about our second pillar, genetically resistant plants? Surely a plant that's labeled resistant is just resistant, right? Well, it turns out our whole definition of resistance was, let's say, a little incomplete. So you can just imagine the confusion, right? A farmer plants a variety of potato that's been rock-solid resistant for years, and then one season, boom, it gets completely wiped out by late blight. How is that even possible? Was the label a lie? The answer, as it turns out, is way more fascinating, and it has everything to do with the pathogen. Okay, here is the absolute key insight. Resistance isn't some kind of innate superpower a plant just has all by itself. No, it's a very specific defense that works against a very specific version of the pathogen. It's like a key in a lock. The plant's resistance is the key. But if the pathogen comes along and changes the lock, well, that key is suddenly useless. And this slide shows exactly how that plays out. So in scenario A, you've got your local potato variety, and it's perfectly resistant to the local pathogen. All good. But then look at scenario B. Global trade brings in a new strain of the pathogen from somewhere else in the world. And just like that, that same resistant plant is completely defenseless. And this isn't just theory. Research in Israel showed this exact thing happening, where imported seed potatoes brought in new pathogen populations that the local varieties had just never seen before. All right, on to our third and final pillar, our chemical defenses. The strategy here seemed so simple. Just rotate your fungicides to stay one step ahead of the pathogen. But once again, the pathogen proved to be a much, much more sophisticated opponent than we ever gave it credit for. So scientists discovered this thing they call dynamic resistance. And this is just incredible. It means the pathogen can basically switch its resistance to a certain fungicide on and then just switch it off again. literally like a light switch. It isn't always a permanent, hard-coded genetic change. This just completely blows up our rotation strategy because the pathogen can just flip its defenses back on the second we start using that chemical again.
And sometimes the resistance isn't dynamic at all. Sometimes it's hardwired and it spreads like wildfire. Just take a look at this chart from Denmark in 2022. There's a specific strain of the pathogen, EU43, and it's completely resistant to a really important fungicide. And it didn't just show up, it became dominant, making up 64% of the entire population. I mean, your perfectly planned fungicide rotation is totally useless if you don't know that the main enemy you're fighting is already immune to it.
So, yeah, all three of our pillars have pretty much crumbled under the pressure of this rapidly evolving pathogen. That old static rulebook, it's obsolete. We have to completely change our mindset. We have to move from just giving these fixed commands to having a dynamic, ongoing conversation with what's actually happening in our fields. So let's just recap what's really changed the game here. There are four big things. First, the climate is getting more variable, which makes those weather-only models super risky. Second, global trade. It means you're not just fighting a local bug anymore. You could be fighting one from halfway across the world. Third, we now know that fungicide resistance isn't a simple on or off switch. And finally, a plant's genetic resistance. It only means something in the context of the specific pathogen it is facing right now. So what does this all mean? It means we need a whole new paradigm. We have to move away from a simple checklist and into a continuous cycle. First, we have to actively monitor what's actually out there, the spores floating in the air, the specific genetic strains. Next, we have to interpret that real-time data to truly understand the threat we're facing today. And finally, we adapt. We adjust our strategies, what we spray, what we plant, based on that living, breathing information. And this quote just nails the whole shift in thinking. See, the illusion was never that our procedures were wrong. They were technically correct. The illusion was believing that just being correct was enough. In a complex adaptive world like ours, stability doesn't come from a fixed plan. It comes from a constant, intelligent flow of information. You know, when you zoom out, this story is about so much more than just a potato disease. It's really a lesson for how we manage any complex system, whether that's a national economy, a viral pandemic, or our own climate. The systems we're trying to control, they're talking to us. They are adapting, they're evolving, they're responding to what we do. Control is no longer a checklist you can just tick off. It's a conversation. The only real question is, are we finally ready to listen?